calculating equilibrium compositions. We're especially interested in this chemical equilibrium associated with like a dissociation reaction. So here's a dissociation reaction where you have A and B, and then you can have C and D, and you can have all four of them, A, B, C, D, in some equilibrium state, all present at equilibrium. The double arrow, like this, or sometimes like this, and like this, that indicates that's reversible. And if you change the temperature or you change the pressure, you could shift it to be more forward such that you would get more of C and D in equilibrium, or you could shift it backwards and get more A and B in equilibrium by changing the temperature and changing the pressure. Normally, increasing temperature shifts it this way. But that's the way they wrote the equation. They usually write it that way, where increasing temperature, and if you look at the table for the log of base 10 of those Ks, they start large negative at low temperatures and increase in value. So as you go up in value, the K is getting larger. Hence, it shifts it more to C and D, more C and D. How about pressure? Well, it really depends on what's happening, because the pressure is affected by this exponent. And this exponent sometimes is 0, sometimes it's negative, a lot of times it's either positive or 0. Okay, so let's take a look at this case right here. It's CO2 with H2 goes CO and H2O. Is it balanced? Is there 1, 1, 1, and 1 for the stoichiometric coefficients? Is it balanced if 1, 1, 1, 1, or do I need a half anywhere or 2 anywhere for those coefficients? It's balanced and everything is 1. So if you look at this exponent up here on that pressure, what is that term? 0. So does pressure affect the equilibrium composition for this dissociation reaction? No, it won't. It won't affect it. If you come in with another one, let's do CO2, CO, 1/2 O2. Is that balanced? Look balanced? Okay. How about this is a 1, that's a half, that's a 1. So if you look up here to be 1 plus 1, 1 plus a half minus 1, it'll be positive 1/2, true? So if P is increased, if P goes up at constant temperature, so this is the only function of temperature right here, so K is a function of temperature, that side stays equal. The left-hand side doesn't change in value. The right-hand side's a product of these n's to the power, to the power, to the, but this P to the 1/2. So if P goes up, increases, doesn't this go up? Doesn't that right there, what I just circled, this term right here, doesn't that go up if pressure increases because of the positive 1/2? So if this is constant and this goes up, what does this have to do? Has to go down, right? Because the multiply equal to a constant. So if it's going down, the numerator is smaller, decreases. So it's like the amount of C and the amount of D decreases, it pushes it backwards. The equilibrium is more shifted toward what's on the left side of the equation, or backwards, not forwards in the reaction. Hopefully all that made sense. Did you follow the logic? It's multi-stepped and a little complicated, but that's the logic. Well, sometimes you'll see a single arrow, not just a double arrow. You'll see a single arrow, and that indicates that the reaction goes all the way. It's a complete reaction. Okay, we use both of them. We used the single arrow primarily in the previous chapter. This chapter with this dissociation reaction, we use a double arrow, but we use both of them in the next problem that I'll solve. Don't forget where to get our log base 10 of the Ks, and we'll be taking a look at this equation, which is dissociation of CO2. We covered the theory. The theory is deep, intense, multi-stepped, rigorous. I tried to do a decent job of it. I posted it on the internet. Please take a look at that. But the bottom line is you get this equation right here. What is this equation? It's our equilibrium, chemical equilibrium equation. And as the temperature changes, the function of temperature, or the pressure changes, you can shift the equilibrium composition of our gas. Now we're going to talk about equilibrium flame temperature. Before we had, in the previous chapter, adiabatic flame temperature. So in review, we had a reactor, and we brought in some fuel, typically air, to mix with it. All of this came in at 298 Kelvin, 1 atm. And what came out were the products. And they came out hot at the temperature adiabatic flame. This was insulated, there's no work, hence it was the highest temperature coming out. And we calculated it where the products were. If you're burning a hydrocarbon fuel, the carbon goes into the CO2 and the hydrogen of the hydrocarbon fuel goes to H2O, and then nitrogen goes along. Typically you quote the adiabatic flame temperature for stoichiometric 100% theoretical air. You don't have excess or deficient air. It's perfect amount of air, just the right amount. Well, what's the difference now with the equilibrium flame temperature? Well, we still have a reactor. The reactor is well insulated. We still bring in the same fuel. We still bring in the same amount of 100% theoretical air. We still bring it in at 298 Kelvin and 1 atm. All of this is the same. I should put 100% theoretical. 100% theoretical air. Okay. But what we do have products come out, but the products are at a lower temperature, the equilibrium flame temperature. That temperature is less. Why? Well, it tries to make it all into CO2, but CO2 can dissociate into CO and O2. True? And it tries to go all into water, but the water can dissociate also in the hydrogen as well as oxygen. And the hydrogen that's there could similarly dissociate into just H, and then maybe recombine with something else. And the nitrogen could dissociate just into N's. So these are like the primary, oops, I should leave this guy off the list of the primary products, but you get some others because of dissociation. And these, when you take a look at the dissociation equation, CO2, CO plus 1/2 O2, that equation is endothermic. What does that mean, endothermic? It consumes energy or takes energy, right? It doesn't produce or release heat. And so basically the dissociation of CO2 took some of that thermal energy which made the products hot and keeps it into a chemical form instead of an internal energy form of hot gases. All right? Likewise, all these other reactions that I wrote down, like H2O is to H2 plus 1/2 O2, that's endothermic. Another way to look at it is if I had CO, I could actually put that into a reactor as if it's fuel and burn it, and it would release heat. So it's like this is uncombusted part, or partially combusted. The hydrogen is a great fuel, right? It's just very expensive. We don't use much of it. But you can combust hydrogen, and when NASA wants to throw a rocket up, that's what's blowing out the back of those not jet engines, what are those, rocket engines? They have pure oxygen, pure hydrogen, and mix and burn, and woof, you have a great thrust. It's just expensive fuel. So this is still like a fuel. So there's a couple ways to think about it. That you still have The dissociation's endothermic, so it takes some of the heat away, so that keeps the product temperature lower. Or you could think of, hey, there's still some ability to combust. There's still some fuels left in the product that can combust and release more heat. So the bottom line is that the equilibrium flame temperature is less than the adiabatic flame temperature. Bottom line. Can we calculate that equilibrium flame temperature? Glad you asked. Let's do it by solving a problem. And this is the last slide for the day, except for I'm going to also do it in Excel. So it'll be a while solving this problem. So we have methane at standard temperature and pressure enters an insulated reactor operating at steady state and burns with 100% theoretical air at the standard temperature and pressure. An equilibrium ideal gas mixture of not just CO2 and H2O and nitrogen. I left out nitrogen. Nitrogen goes for the ride with the air, doesn't it? But they have CO, it's like uncombusted carbon with the methane, as well as unused oxygen. So those are the unused parts, or the disassociated parts of CO2. Okay. Determine the temperature of the exiting products. You need to calculate the equilibrium flame temperature. Why equilibrium? Because it's in chemical equilibrium and there's dissociation of CO2. Now, is there any way that they put anything in here like H2 is part of the products or HO is part of the products? They didn't list it. So even though I said H2O could also dissociate, it's not called for to model that in this problem. So don't model it. Only model the dissociation of CO2. If they would have listed, okay, we get some H2 in the products, well then you have to consider it. Also, they didn't list any dissociation of N2, so N2 just goes through the system. After we calculate for part A the equilibrium flame temperature, then compute the composition of the products. So we want the mole fraction of CO2, the mole fraction of carbon monoxide, the mole fraction of oxygen, the mole fraction of water vapor, and the mole fraction of N2. That's what we're asked to solve. How do we approach this problem? Start off with 100% theoretical air combusting with methane. So CH4 with our O2 plus 3.76 N2. And it goes to, and just do it for complete combustion. So it goes to CO2 plus H2O with a 2 there, plus, and then we come back with a 2 here, and we'll have 2 times 3.76 N2. Is that balanced for 100% theoretical air, assuming complete combustion and no dissociation? You like that? Thumbs up? Good, you're all with me? Good, good. So now what do is we think about these being our reactants and these being the products, but in the products modify that right-hand side to account for some dissociation of CO2. Well, how does CO2 dissociate? Come up here and remind ourselves that CO2 dissociates by this equation, carbon monoxide and 1/2 O2. That's equation, it's in our tables. We can get the K value, the equilibrium constant for that equation, right? And that's why it's an equilibrium. It's chemical equilibrium. True? So what we do is we leave the right-hand side alone, CH4 plus 2O2 plus, I'll write it a little different. I'll write it as 7.52 N2s. It's a little cleaner to do coefficients in front of each term. And then we'll have the CO2. And I'm going to think about, I started with 1, but if I have so much disassociating, that's what I'm left with. So what is Z? Z is some amount of CO2 that disassociates. So it's the amount of CO2 that disassociates. Okay? So that's why on the right-hand side for the products, we have 1 minus Z. Now we're going to come over here. If Z is the amount of CO2 that dissociates, it's going to produce some CO. But what coefficient goes in front of that CO? Z. Now that was hard. Now the really hard one. You have O2. Right? What coefficient goes in front of the O2? Half Z. True? You see that? That's complicated, right? Because it's like, you have Z is the extent of the dissociation of CO2. If Z is 0, I have no O2. If Z is 0, I have no CO. Let's say Z is 1. If Z is 1, I have no CO2. It all disassociated. And then I'll have 1 CO, but only a half of O2. Got it? Maybe some of you are like, hey, this is so easy. Like quality? Yeah, something like that, yeah. So this was the hard part. We still have the 2 H2Os going along because the hydrogens need to balance. And we still have the 7.52 nitrogens going along. Now we're ready to write down our equilibrium equation, our chemical equilibrium equation. I write it something like this because I'm going to do for the equilibrium frame temperature, it has to be in chemical equilibrium as well as satisfy the energy balance. So there's 2 equations that are going to come into play. But let's just get the first one. It's our chemical equilibrium equation that deals with the composition. So what happens is we have K. It's a function of T. It's equal to, and then I look over here and I have the number of moles of CO raised to the power 1 times the number of moles of O2 raised to the 1/2 power divided by the number of moles of CO2 raised to the 1 power. Then I have the pressure divided by 1 atm divided by the total number of moles in my gas mixture. Then I have it to the 1 plus 1/2 minus 1 power. I just applied our equilibrium equation we've done before. Did I go too fast? Did I lose you, or are you on track? Thumbs up if you're on track. Now we have to adapt it more, okay? We're adapting it more to our particular problem. For our particular problem, the number of moles of CO is Z. The number of moles of O2 is Z over 2. Then we still have to put that to the stoichiometric coefficient in front of this dissociation reaction, which is a half. And the number of moles of CO2 is 1 minus Z. The pressure is 1 over 1. It's atmospheric pressure going out, so it's just 1 over 1 atm. But that total N, this total N right here, I have to work with a little bit. So let me kind of tuck it in right here. Is the total N, is that the number of moles of CO2 plus the number of moles of CO plus the number of moles of O2 plus the number of moles of H2O plus the number of moles of N2? Does it account for the N2 and H2O in our products? It does. And they are considered inert. So if you see the word inert, that means they're just not participating in this reaction. They're not disassociating, okay? But they're interfering with it, and so they come into play. So what happens is this is, if I write it out, this is 1 minus Z, this is Z, this is Z over 2, this is 2, that looks like a Z, but it's a 2, and this is 7.52. See that? So when you sum it all up, N is, let me write it here, 10.52 plus Z over 2. That's what total N is. Did you follow? You okay with that? It's like this 1 minus z cancels with that 1 minus z, so I have a 1 plus a 2 plus a 7.52. That gives me the 10.52. And then I have a z over 2 left over as well. And now I raise it to the power 1/2. True? That equation, it depends on the temperature. But primarily, z can be determined before this lecture, if temperature was given, you went to the table, you got the K, you got this equation, you said one equation, one unknown, let's solve for z, and I'll get my equilibrium composition. But we don't know the temperature. So to get the temperature, we have to go back to the previous chapter and do the energy balance. So the previous chapter said, for an adiabatic reactor, that term 0, is equal to the sum over all the products of the stoichiometric coefficient times h bar minus the sum over all the reactants, the stoichiometric coefficient h bar. How many people remember that? 0 is equal to, does it look familiar? It's our energy balance. Don't forget, 2 balances. One associated with chemical equilibrium, one associated with energy, first law. Now we're going to this first law, energy. So this equation looks like 0 is equal to, let me write it out, okay? The number of moles times, let me kind of write it out like this. The number times the enthalpy of formation plus the enthalpy at the equilibrium flame temperature minus the enthalpy at the reference 298 temperature, all of that for the, actually it's more like everything here, for each product. First product would be CO2. Then you would do the same thing. You would say N times the enthalpy of formation plus the enthalpy at the unknown equilibrium flame temperature, that's the product exiting temperature, minus H bar T ref. And that's all for the second product, which is CO. Then I have to do N times H bar for, and I didn't expand it, but this is what expands it, enthalpy of formation plus enthalpy at the outlet temperature minus the enthalpy at the, should I write it all out? I kind of get tired of writing it all, but H bar equilibrium flame minus H T ref, close parenthesis. What's our second? It's not CO, it's O2 plus, hey, we didn't even get through the whole list of our products, did we? The same thing for our H2O plus the same thing for our N2. Now we finally get to the minus for the reactants. For our reactants, we had N times the enthalpy formation minus the enthalpy of the incoming minus the enthalpy of the reference temperature. Okay, bar, 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 put a bracket and a bracket. And the first reactant is CH4. And then we have minus N O2 minus N N2. All of these, the O2 is our reactant and the N2 is our product. I mean our reactant. Both of these are reactants. Okay. Does all that make sense? I didn't write it all down, but does it make sense? Somebody's following some others. Are you with me? You got it? All right. A lot of these terms are 0, like the enthalpy formation of nitrogen is 0, the enthalpy formation of oxygen 0, the delta H on the oxygen because it comes in and it goes in at the in and the reference are the same temperature, 298. For methane, that delta H is 0. The enthalpy of formation of methane is not 0. So that's really the only term. But what is that coefficient in front of for the methane? 1. The coefficient in our equation is just 1 coming from right here. Okay, let's come up here to O2. Enthalpy of formation of O2 is 0, but this is not 0 because we don't know that the equilibrium flame temperature, and the same for the H2O, same for the nitrogen. So this is now almost beyond tedious. So when you get to tedious, you jump to Excel. Can I solve it the rest of the way in Excel? Okay, let's do that. All right, so we come to Excel, and I like to just start and say, I'm trying to look for the equilibrium flame temperature in Kelvin, and I anticipate having to iterate. It may be 2000 degrees Kelvin. It may be 1800 Kelvin. That is where I'm going to finally get the solution, but I'm going to have to iterate to get it. You'd have to iterate by hand. Let Excel do the iteration for you. Also, Z was an unknown determining value. Maybe it's 0.1. What was Z again? It was the amount of the CO that disassociated. True? So it's not going to be above 1. But maybe it's 5%. Maybe it's 0.05. Maybe it's 12%, 0.12. Whoops, 0.12. But it's some value. So those two, and I like to color code them so that I know those two are things I'm going to iterate. To solve first for the chemical equation, the chemical equilibrium equation, I'm going to need to get K. I'm going to need to get K as a function of temperature. True? I remember my table, so I want Excel to be able to do that for different values of K. If I put in 1800 in that cell, or 1900 in that cell, or 2000 in that cell, I want it to automatically get the K for me. That means I really have to get the data out of the table, copy it, type it in and copy it, and get it into Excel somewhere. And so I'm just going to put it in the same sheet over here to the side. And so this is for the CO2 dissociation. You can check it. The temperature's here in Kelvin, and this is the log base 10 of K. It starts large negative and gets more larger as we go along, okay? Well, to do that, what I'm going to do is I'm going to get the log base 10 of K right here. It's a function of that temperature. I use two calls. Maybe you're a pro at Excel. Maybe you know how to do this better than me, but I'm going to show you one way to do it. And the first thing you do is find a percent rank, and we're going to do it for inclusive. Now you can read more about this routine, but that's the routine. And since I'm coming in with temperature, I need to know where that 2000 falls in this range of temperatures. So in that given array, see the array, that's my array, I want to know where this value of X, 2000 or temperature, falls. And significance, you can read more about it by just clicking, but put it to be like 7 because it's the number of significant digits that it does the percent rank in, okay? So if I do that, 2000 is about 37% of the way through the data set. 500 is about 4% of the way through the data set. 298 is 0% of the way through the data set. And 3,500, what do you think 3,500 is going to be? Come on now, 100% of the way. Okay? So that's what you're doing. You're finding the percent of the way. The next thing is I want to take that value and get this one. Okay? Because these aren't in equal increments, are they? 298 to 500 is not an equal increment. It's not equal size steps. So it took me a while to figure out, do some Google searching. This percentile.inc, inclusive, right, of the array, this is the array that I want the value back out of, comma, given k, which is that input. And so if I get 3,500, it returns 0.19. Let me click over here some digits. 0.190. Let's check it. 3,500, 0.190. See that? Let's check the lower end, 298. And you get negative 45.066. Got it? Let's say it's 400. It's going to interpolate between these two. And so that's kind of helpful because we don't know the temperature, and it's not going to land perfectly on one of those lines in our table. So now we have that log base 10 of k. So now we want the equation, the equilibrium, chemical equilibrium equation, and we want that to be equal to 0. But it's a function of this k. So it's a function 10 to the exponent of that power. That's now k, right? Because I had to 10 to the power of that coefficient. Then minus, we wrote that equation out. What was that equation? It was z times square root of z divided by 2 divided by 1 minus z. Then we multiply times the pressure, that was 1 over. Then in the numerator we had that funny 10.52 plus z divided by 2, close parenthesis, that's 1 over that, close parenthesis I could put right here to 0.5, or I could just come back here, come back here and take the square root of it right here, SQRT, square root, right? But there it is. So if the equilibrium flame temperature was 2000, this would be the log base 10 of that equilibrium constant. It would not be balanced because this z doesn't satisfy that equation. If I want to find the z that makes the chemical equilibrium equation balanced, I would go under Data tab right here, go under What If Analysis, go under Goal Seek, and say this cell C4, it's given this dancing box right here, I want to set that value to 0 by changing this value right here, and it'll iterate it, and that Excel says that's close enough to 0. Sometimes I don't like that. I say that's not 0. So I take 1,000, and multiply everything. And what that did was it made it closer to 0, and then I drive that to 0 again. What if, goal seek, set that to 0. What cell again? I need to get that cell, C4, not C5, right? Set it to 0 by changing cell C2. And there you go. See what I did? It's like Newton-Raphson secant method. Root finding. You have to be able to do something like that with your calculator for the final exam. True? Talked about that last time. All right, now that's half of the problem because we don't know the equilibrium flame temperature. It could be 2100. And if it is 2100, then I got to go rebalance for the chemical equilibrium. Now we've done the energy before. So as you might think, I solved this problem before coming into class. I'm going to go to a sheet and grab it, but it's parts that you've seen already, or I've tried to show in lecture if you were in the lecture. So if I come over here and I grab this without you looking at too much, and I copy and I run back before you look at too much, and then I paste it, now I can explain it. So what do we have for an N? It's methane, oxygen, nitrogen. Those are the coefficients on the N, true? What about the outs? CO2, CO, O2, blah, blah, blah. The CO, it's 1 minus Z is what's coming out. So it depends on what is in the cell C2. And likewise, it's Z for the amount of CO coming out. And it's Z over 2. But 2 is 2 for the H2O coming out, and 7.52 is that going out, right? If you sum them up, we'll do that later. But you use the enthalpy of formations. You have to type those in by hand. And then this temperature right here is brought down from the temperature up here. So if this changes to 2200, everything in the blue gets updated in the energy calculation, because it calculates the enthalpy for the CO2 as a gas as a function of that temperature, enthalpy of CO, enthalpy blah, blah, blah. Does this look familiar? Do you need to look at it some more? Do I need to explain it in more detail? So the sum happens over here where you have the product N times the enthalpy of formation plus enthalpy in minus enthalpy ref, which I just left blank because they're both at 298. And so this is the only on the sum on all of the reactants coming in. The products, though, you do have to have the enthalpy exiting, and that's different than enthalpy reference. You have the enthalpy formation, then you have the coefficient N in our equation. And then when you sum them all up, you get this term, true? So what we want is we want to have something like this. Equation for thermal or energy equation, where this was the chemical, CH or C for chemical equilibrium. This is thermal equilibrium. How's that? Let me come back here. Thermal equilibrium, okay? So that would be the sum of the products minus the sum of the reactants. That term should be 0. It's a function both of T and Z, but it's primarily a function of T. Let's do what if analysis, goal seek. Take that cell that's dancing, set it equal to 0 or drive it to 0 by changing this temperature. So it says, okay, it's closer to 2307. But my chemistry is now in the equilibrium, is it? So I come back and I say goal seek, and I say drive that value to 0 by changing this. And then the energy is not in balance. So you do goal seek, drive it to 0 by changing the temperature. And it goes back and forth, back and forth. But there's another routine, so I get a total error. So the equation, EQ, C, I'm going to square it. Then I'm going to add to it EQT quantity squared. Does that make sense? And so it's like this is equal to this amount squared plus this amount squared. All right, it's a pretty big number. Let me try and make it look a little prettier. Oops. All right, and you can see that if I drive this one to 0, data, what if, goal seek, set the value to 0 by changing Z, okay, that it upsets the energy balance, and then this number is no longer close to 0. True? But I'm going to do this, what if, goal seek, to the value 0 by changing the temperature. Somehow it looks like we're getting close to a balance equation, but at this point you can come over to solver. I don't know why they have goal seeking here under what if analysis and solver over here, but you sometimes have to do the add-in for solver separately. Anybody used it? But what this is once you get this open, you can say I want to take the cell C19, that's my objective. I want to minimize it or maximize it or make it a value of this. Minimize it by changing, and the key is by changing variable cells as a plural. I can change both of those. It'll start to change both of those to try to drive that one cell to 0 or minimize it. So good luck, because this always doesn't work because it's nonlinear. Sometimes it works. If you have a good starting point in numerical methods class, a lot of times your algorithms will converge. You have a way off starting point, nonlinear root finding team, it won't converge. Let's see if it'll converge. Let's try that again. Solver C19. Solve. Solver found all constraints are satisfied. Well, let's do this. Let's change this value to 2250 and 0.105. All right, now let's see if it'll do a solve. C19 solve. Okay, that looks pretty good. Okay, now I could play with it a little bit. I look at this value. I want that to be 0. I already boosted its magnitude by 1,000, right? I look at this value. Oops. Yeah, that value. That's pretty good. Negative 0.5. Remember all these big numbers over here? So the energy balance is pretty good. The equilibrium balance looks like it's pretty good. So this is pretty good. I wouldn't trust that many digits, of course not. So we'll clean it up a little bit, maybe that much, and come over here. Something like that. Or that's good to 3 digits. This is way too many still. So that's how many Kelvin? Temperature? 2262. I wouldn't even trust it to that. I'd say 2260, 2260, something like that. And then, you know, it's sensitive, so maybe I should go back, leave it alone, because now that's 0. But there's your solution for the temperature, the final outlet equilibrium temperature. You can even box it. True. What about the fractions? You can just put your answer over here, y, where y is the amount of CO2 divided by the sum. Put that $sign. Drag this down for all of them. Make sure the sum goes to 1. Just to double check, it does. Maybe I want to put those as percentages, and so I can read it. So the nitrogen in the product, 71.1% is nitrogen. 18.9% is water. 0.5% is oxygen. About 1% is carbon monoxide, and 8.5% is carbon dioxide. So there's your other part B. True. So that's how you solve this problem in Excel.